So today I'm going to talk about control flow integrity, which is something that I've been looking into recently. So let me get started with the definition. So control flow integrity, or CFI for short, is about limiting the runtime control flow of the application to a predetermined safe CFG or control flow graph. So we typically derive this control flow graph doing static analysis. So this safe CFG basically consists of control flows, which are like with some statically determined safety properties. For example, callees should always return to their callers, or either they should transfer control to a function in case of an error call, or the calls, or like all the direct or indirect calls should target non-functions. So why do we need to do that? Like, it sounds a little bit restrictive, right? So people use this technique so that like, it sort of prevents a certain class of attacks. For example, if you take your standard buffer overflow, in that case, an attacker would like overwrite the return on the stack so that it would like point to some kind of a malicious code buffer, potentially on the stack itself. So when the function returns, it will return to this malicious code and do some funky stuff, and before you know it, the attacker has the control of the application with access to a root shell, for example. But fortunately, in modern operating systems, you cannot do that kind of standard basic stack overflow attacks because they feature this security mechanism called data execution prevention, which makes the stack non-executable. But in like recent like advanced attacks like return-oriented programming and return to libc, the attacker does not even need to like generate new code. He can like basically reuse the existing program text or the code in shell libraries, for example, in libc. So, for example, in return-oriented programming, depending on how you sort of overflow this stack, like how you set up this stack, you can like chain these returns to go into like some existing functions, for example, in libc, and sort of stitch together a sequence of instructions which can be used to do something sort of nasty, like call into some dangerous system call functions, for example, and which can ultimately result in gaining root shell access. So going back to why we need CFI, so in all of these attacks, the common theme is that the attacker hijacked the regular control flow of the application. So what CFI tries to do is to sort of detect this kind of irregular control flow and sort of fail fast if that happens. So how do we do it? So basically the idea is to, again, constrain the control flow. So for direct control flow, it's easy. We can even like statically verify if the direct call is going to a safe, so because like the target is like there, like, but in indirect control flow, we do not know the call target because it's only known at runtime. So for that, we need to insert some runtime checks in the code. So we basically need to instrument around indirect control flow instructions, basically. So if you take like an indirect jump or a call, then we do something like this, where we compare the jump or call target against the set of safe targets that we sort of determine to be safe using our safe control flow graph. And if not, then we basically go into an error state. So same with the return, we check the stack return with our safe target set, and if not, we fail. So this approach is not without its limitations, as you might have imagined. So typically, like we sort of tend to approximate the actual runtime CFG in our static CFG in order to become conservative, because For example, in indirect calls, we say like, okay, an indirect call might like jump to, or like a transfer control to all the non-functions in the program, but it's not true in reality, right? I mean, it might just like go to like one or two functions, for example, in virtual method dispatch, but we don't know because it happens on runtime and we don't know what happens on runtime. And also, it does not consider runtime loaded code like shared libraries. So that's like a big limitation with this static control flow enforcement. So I'll read this limitation for a bit at the end as well. So another related concept to CFI is software fault isolation, or SFI. So this is basically sort of executing unsafe extension or plugin code without compromising the security of the application itself. So in another word, you might be familiar with the sandboxing. So sandboxing is like where we frequently use in browsers, for example, to like load and execute unsafe extensions. So the idea is like to make sure the effects of the extension or the plugin are confined. For example, in Chrome, they used to use this thing called knuckle, but I think they've deprecated that now in favor of WebAssembly. So in there, the idea was like the extension is like allocated an area of map memory to which it could read and write, but it cannot do anything outside that sort of allocated memory area. So for that, we need to ensure that all the memory operations of this plugin or extension do the right thing. So we basically sanitize the memory loads and stores to be confined within this range. So what they do is like to either mask or verify each and every memory load and store within the this extension. But the thing is, like, we also need something else to make this work. This wouldn't work as it is if we just like sanitize all the loads and stores. This is where again we need CFI, because without CFI, an attacker can like bypass these memory sanitization instructions using like hijacking the control flow. So in knuckle, they use like a CFI approach which is sort of coarse-grained. So knuckle is like a compiler-based toolchain where like you have to compile your extension using knuckle-enabled compiler. So the compiler basically ensures that all the basic blocks start at like 32-byte line addresses, and it uses like knobs to like make the element happen. So any jump target, indirect or direct, is masked to be 32-byte line. So you cannot like jump in the middle of a basic block, for example. So this is called a line chunk CFI. It's not super precise, but it reduces the attack surface by reducing like the number of targets that you can jump into in the coarse range. And I think they also use like an additional security mechanism in conjunction with that, so it sort of works out fine, even though it's like not super precise, but it's like low overhead than like if you had to like precisely control the control flow. So why is it interesting to me? As you might know, like I've been working on lightweight runtime binary instrumentation techniques. So there are like two ways to enforce CFI. The first way is to do like static instrumentation, either by using compiler support or doing binary rewriting. The problem with that approach, as I mentioned earlier as well, is that it's static. Like it does not include the runtime information. Like it cannot account for shared libraries, for example. The other approach is like using dynamic binary translation, and that can like basically account for any like runtime loaded code. But the problem is that it incurs some non-trivial overhead during this binary translation process. So what I'm right now looking into is to sort of combine these two approaches, like where you sort of statically instrument as much as possible, but whatever you miss from that, like you use like lightweight runtime instrumentation to sort of sanitize dynamically loaded code like in shared libraries and sanitize those code for CFI as well. And I'm also looking into a couple of other techniques which could potentially lower CFI overhead due to instrumentation, but it's still very experimental at the moment. So I think it might be another talk, hopefully, if it works out. So yeah, so that's about it. So the summary is CFI trends measures control flow context, and its basis for other techniques like sandboxing.
All right, we've got about 4 minutes for questions. Set up.
Buddhika, you said there was overhead from CFI. Can you give an approximation for how much overhead it typically adds to a program?
Sure. Yeah. So over the years, like there've been like many implementations of CFI after the original paper. I think it was in 2005. So yeah, overhead varies like widely from like different implementations, but like the lowest implementation I found was around having like 5%.
Okay.
Of like, I don't know, it's just like on spec benchmarks though, but like they hadn't like, I think, evaluated in like real life applications, like mostly it's the case like in these kind of papers, but yeah, 5 to 10, I guess.
Okay.
Any more questions?
All right, let's thank Buddhika. You ready to go?
Yeah.
All right, let's go.
So we're going to do completely opposite to what Buddhika talked about. We're going to allocate memory at runtime, put some binary in there, jump to it, and run it. So these are like my goals of this talk, and this is like something I'll go to each point and I'm going to talk about it. The first is we're going to look at a metacircular interpreter, which I believe most of people here have already looked at. It's like a small scheme language, and we are going to evaluate it in Racket using Racket's functions. So we are going to evaluate a lambda using Racket's lambda, evaluate plus using Racket's plus, let using Racket, let all those things. And then we are going to add a just-in-time compiler for some of these things, right? And adding a just-in-time compiler, we're going to do it in a way which is more iterative. We are going to add things step by step. We are not going to add the full compiler one at a time. And what it does is, it gives us this technique of going back and forth between our interpreter, which we have already written, and our compiled code. And this is like one of the main points which I want to focus on in this talk, is you have a compiler and you have an interpreter. You don't want to compile all the things right now because you're in the middle of doing something and you want to see how it goes. And so you want to be able to like change stuff in both of the things and go back and forth and do all of them. So we're going to be focusing on like what we are compiling is correct. Our metacircular interpreter is doing what it's supposed to do, and mostly the iterative process of improving the compiler. And all these things we're going to ignore. I'm not going to talk about performance. I know like a lot of time you see just-in-time compilers, it's going to be like, okay, this improves performance. No, I'm not going to do it. Garbage collection, yeah, I'm not going to worry about garbage collection. We're going to allocate memory and forget about it. And anything else that you think of when it comes to your mind and it's not related to the things I talk about, we're not going to do it. So we have 5 evaluators, and we're going to go one by one and look at each of them. So let's do this. So can everyone see and read?
A little bit.
So this is our interpreter. Very simple interpreter. We have a lambda. compile to lambda, if, compile to if. I added letrec just to be able to do some interesting stuff. And our environment is a list of mutable cons. So we can go and just modify it just for the letrec. And then we have application, and our function application is again like evaluate our later and apply. And these are like a bunch of things that are used in all those. So let's go and add an compiler. Now, where do we want to start? The easiest thing sort of start is we are going to compile our lambda to a closure using LLVM. And we are not going to do anything else. We are just going to compile a function which takes a number of arguments, one for environment and all the arguments, and it's going to call the evaluator back with the whole body, extending the environment with. So we had this before. Instead of this, we are compiling our closure, which is our full lambda, currying it with the environment, because when I'm compiling it, I just add environment as the first argument, and then just giving it back. Now, how is this done? I'm going to show you stuff which doesn't show you all the ugly stuff I've done, just the pretty parts. So we have this lambda that we are trying to compile. And we create a sim for environment. And the language we are using to compile is sort of like C. So it has explicit returns. It's not an expression value. So we also want to like sort of massage our expressions to have like series of sequence and return stuff. And that's done using like you go recursively pass a function to return. And so we start with our lambda. I'm using my framework that I've made to do all these kind of things. It's called sham because it's a sham. We make a function. We say, okay, this is our ID, and we cons our environment to our variables. So this function it takes a hash with sort of like meta information we want to give for optimization, not going to worry about it. Name of the function, the symbol of arguments, the types of those arguments, the return type, and the body. So when we are compiling our code using x86, we want a type. And we are going to do what Racket does. Racket has a single type for all its objects. It's called scheme object pointer. And it's just a pointer to stuff. And for integers, it just bit masks first 3 bits, I think. And we are going to do the same. I'll show you what this JIT type is. For now, just think it's there. And so now we have the body of the function that we're going to do. And we just say, call a Racket function, which is eval, which is up there. This is our expression, which it's a symbol, so we're going to convert it into a pointer to that symbol so that we can compile it directly to x86. And we are going to extend that environment in the compiled code because we want to give all the function arguments that are there. And then we're going to do it. So now I have these tests. Only going to worry about these. So all the tests pass, we don't have any errors in this connection. I added the print information to show stuff around there. Yeah. So these S expressions that you're seeing on the right side, define closure, that's the sort of the sham language that you're seeing, and that's what we are doing. So we have, this is like the simple function, I think this one, or someone. And we have a single argument. Go inside. So this Racket function is eval, and we call it using these are JIT values, which are converted to a big I64 number, casting those to pointers and calling them. And we have our right? This is our simple function. And we can see, if we want to dump the whole module, we can see our LLVM IR. So we are doing the IR allocating stuff and then calling things. And so if you see these operations, once we have that S expression thingy that we made, we're just going to say compile this module. That's Sham's function. It says compile this module. Module takes a list of functions that you want to compile and some types if you want to have more types. And then initializes it. You can optimize it using like the same optimization level that you have in GCC and Plan. And then we are going to get the function and wrap it. What wrapping does is, because when we get the function, we're only going to get the pointer to the function, and we want to wrap it in the Racket value. So if you see the types, the JIT type is just an I64. It's not even a pointer, it's an I64 because it makes things easier to go back and forth. And we have JIT apply and JIT Racket, which are doing all the stuff to go there. And one more important thing is this. We are doing like marshalling and unmarshalling, where cast is Racket gives us a cast to cast things at C level. So scheme is the Racket scheme type, and we are casting it into an integer pointer and back and forth. And that is doing for functions. So now, here we are only doing compiling the function sort of like a shim of a function. Let's compile the rest of it.
That's the time.
How much time is that?
That's it.
Okay.
You're in your question time now.
Okay, we can compile more stuff, but courteous. But the point is going back and forth. You can compile, and this is what we are giving you to call Racket stuff from your compile code, and you call the compile code from the Racket stuff. Questions? If you want rest of the evaluator, we can talk to it. No questions?
Seems to have bamboos with the audience.
Okay, I'm going to show you the last evaluator. I compile if and function application. So here's the if. It's a statement block. We have let values to evaluate the check. We evaluate that check, and ICMP equal is integer comparison. We're just comparing the integers with scheme false, and then building the rest of it. So the if is getting compiled to our actual jump statements in LLVM. And the same thing we do, and one more thing we do is function application. So function applications are also compiled. And to do function application, we are not using Racket's #%app. We are using Racket's C function, which is implemented in Racket, which is all the applications end up to. So like that's the endpoint, which is scheme_compile. And Sham gives you a way of dynamically looking up stuff in your namespace. So we just look up scheme apply, it's a C function, Racket, tell what its types are. You only need to give the return type because we're going to figure out what the argument types are based on what you're doing. And then do that. So now we have two things, if and function application. You can do a lot of other stuff, and we are doing like the looking up of function arguments and those kind of things. Now, no more questions? Time is up.
Last call. Any questions? All right, let's take Rajan.